Hello, everybody, and welcome to section 2.4. Today we're going to look at word problems, essentially. We're talking about right angle applications. You can see on the left-hand side of the screen, I've got, well, I guess that's over here. I've got the book pulled up for some of the exercises to give you some examples. But first we'll go over a little bit of vocabulary definitions, if you will. Now, unfortunately, this isn't a live lecture. This is pre-recorded. This should be the last time that I'll have to miss a live lecture. It's just very difficult to schedule appointments, when they're not between the hours of like 8 and 4. Unfortunately, we're not getting the live face-to-face feedback that we would. If this works out and you guys like the videos, I have made a couple more videos, since last year when we had to do the whole work from home thing. And I can make some more supplementary videos, but from here on out, we'll still have all the live lectures. Videos might just be more on top of that as supplementary, but they won't replace anything. But I didn't want us to fall behind by missing a section, so I wanted to at least get section 2.4 out of the way for you. So if you have questions, feel free to email me, or hopefully we can go over them in the next live lecture a little bit and get to them before the first exam. So let's start by looking at a couple quick definitions. And as we go through these word problems, we'll see a little bit of this vocabulary pop up. So we want to be comfortable with the vocabulary when we read these word problems, of course. So we will say that an angle that is measured from the horizontal upwards is called the angle of elevation. So if we want to talk about the angle of elevation, all that we're doing is we're standing, we're looking at the horizon, and we are looking upwards to, say, like a tall building or maybe a radio tower or something. That is what we call the angle of elevation. When we look at it in terms of the quadrants 1, 2, 3, and 4 on the Cartesian coordinate system, this feels natural, like a positive angle. Positive angles sweep counterclockwise when they're in standard position. We go from the x-axis counterclockwise. Here we're looking at the horizon, not necessarily on an xy coordinate system, and we're looking up. Now, if I were to face the other way over here, and I was looking at the horizon and looked up, it does feel different, like you're almost going clockwise rather than counterclockwise. But it doesn't matter because you're still looking up. So this is where we drop the whole positive negative angle thing and just talk about angle of elevation. No matter what our perspective is, no matter where we're standing, we just are telling the reader, hey, you're looking up at some object. And of course, the vice versa of that would be an angle that is measured from the horizontal downwards is called the angle of depression. Think about when you depress a button, or some people just say press a button, right? That angle of depression. This time we would be staring out at the horizon, but maybe we're looking down a trench or down into the water. Then we're talking about some sort of angle of depression. We still call it the angle with the positive, even though, again, it feels like, well, aren't we going clockwise to look down? Shouldn't that be a negative angle? Well, we don't care about the Cartesian coordinate system here. We just care that we're standing here on the horizon and maybe we're looking into some water to look at the angle of depression to where we can find some sort of little fish swimming around. Obviously, we're not talking about any sort of physics here with like light refraction or anything, but we're just taking a general case of, hey, I want to look down. Doesn't matter where my perspective is. If I'm over here, I'm still looking down. Basically, what we want to do is we want to deal with the positive number that that angle represents. We can either look up 20 degrees, we would say the angle of elevation is 20 degrees, or we can look down 20 degrees, we would say the angle of depression is 20 degrees, not needing to bring in the positive or negative into the picture because we've already said elevation or depression to be clear about whether it's up or down. Again, these are real world applications. In a real world application, you may just not want to have that extra negative symbol around. Also, in the real world, you know, if you speak the English language, you could tell someone, hey, look up, or what's the elevation? Or you can tell someone, hey, look down. Just notice I forgot a D there. You can say, hey, look down, what's that angle? It just feels a little more natural to give them a positive number because you've already stated up or down. So you might see a little bit of that sprinkled throughout the exercises in 2.4. And one more quick little definition, and that is something that, again, you'll see sprinkled throughout 2.4 just a little bit, and that is the definition of bearing. We'll say, not A, we'll say the bearing of a line, we'll call it script L. The bearing of a line L is the acute angle formed by the north-south line and the line L. So basically what that means is we are looking at our cardinal directions. We have north, south, west, east. When we talk about bearing, we always measure from the north-south line, which again feels a little different from looking at the Cartesian coordinate system. An angle in standard position is always measured from the positive x-axis, and then we sweep around positive degrees, or in standard position, positive x-axis. If it's a negative angle, we know to sweep clockwise. We're not talking about that here. We're talking about very specifically projected onto the surface of the Earth, where we have a North Pole, South Pole. We've got west and eastward directions. So we talk about bearing as coming from the north-south line, meaning I could have an object that is traveling north bearing 45 degrees east. And we would write that out, north 45 degrees east. Or if I have an object that is traveling north bearing 10 degrees west, that object is going north bearing 10 degrees west. So we write it out like this. Or if it's somewhere down here, we might say that we have an object that is traveling south and then 60 degrees east. So we have an object bearing south 60 degrees east. Again, notice we're always starting out by saying we're going from the north or south line, and then we tell it how far to go. And again, we talk about an acute angle. So we don't want to say, oh, it's bearing north 97 degrees to the east, or north 110 degrees to the west. Then we're not respecting the definition. We're not giving them an acute angle. So we do want to satisfy the definition by talking about an acute angle. So that is a little bit of terminology that we might come across in a couple of the problems in this section. So the first one that I have pulled up is a nice introduction to looking at an application where we would have a right angle involved, and we can solve based on a little bit of trig functions. And it states that for number 18, I don't want that on the screen. Well, I was going to highlight 18, but it's going to bring that up, so I'm just going to leave it behind. Number 18 asks for the height of a hill, and it says a road trip up a hill makes an angle of 6.5 degrees with the horizontal. If the road from the bottom of the hill to the top of the hill is 2.5 miles long, how high is the hill? So picture this where, and I'm going to exaggerate the angle quite a bit. Well, okay, maybe not that much. That might be a little bit overkill here, but we've got a horizontal, and I've got, yeah, that'll get the job done, a 6.5 degree angle, and I'm looking towards the top of the hill. Now, the hill itself isn't going to be an exact triangle. Realistically, that hill has a little bit of asymmetry to it, and it's probably rounded off at the top, but there is a top of the hill that we can look at. We can look at the road going from the bottom of the hill up the hill. We have to do a little bit of assuming here to simplify the mathematics. We don't have all the tools to measure every little nook and cranny going up that hill, but we can form a right angle by looking at the horizontal going towards exactly underneath where the highest point of the hill is, and then going up to where that road stops at the top of the hill. That road is 2.5 miles. So our task is going to be to find the height of the hill based on the given information that we have. Well, we have a height. Oh, I gotta stop doing that. It keeps bringing that thing up on the screen. We've got the hypotenuse, and we've got the angle involved. We are looking for that opposite side of that angle. I'm just going to call it h for the height of the hill. If this is the horizontal, I want to go straight up and find the peak, the highest point. And I want a trig function that involves the opposite side and the hypotenuse based on this given angle, 6.5 degrees. Well, the sine function gets that done, because when I take the definition for sine of this angle, 6.5 degrees, based on my perspective, I'm looking at the opposite, which is h, over the hypotenuse, which is 2.5. So remember the definition of the sine function of this angle theta talks about the opposite side over the hypotenuse. That is how we define that sine function. Well, now we can multiply both sides by 2.5. That way it cancels out in the denominator on the right-hand side. And now we just have to go to our calculator and say that 2.5 times sine of 6.5 degrees will be equal to h. Now, that is not a nice angle, not a 30, 60, 90, 45 degree angle. So we'll go to our calculator and we'll see what it says. 2.5 times sine of 6.5. Just make sure you're in degree mode, because you are typing in a degree. If you're in degree mode, then you just need to type in 6.5. You don't need to also put in the symbol, the degree symbol. And we'll say it's approximately 0.283008034. Okay, this is the calculator doing its best effort to give us the closest answer to what we've been given. And what we want to do is just sort of line things up in terms of significant figures. Also, how accurate are they being? Now, when we look at something that only has two significant figures for the length of a side, typically we only go to the nearest whole degree. So even the textbook right now is not agreeing with its own self, the way it defined, hey, whole degrees go with 2 sig figs. Well, this is 2 sig figs. Or if this is 2 sig figs, why isn't this a whole degree, however way you want to look at it? I would say h is approximately 0.3 miles, since that's the unit we're talking about. is probably the best answer we could come up with. It really does keep the same level of accuracy as far as going to the 10th place, If you said 0.28, that would be something that you could debate over mathematically, or in physics or chemistry. It just, whatever the teacher says is what you want to go with. But out in the real world, that might not fly. If you're an engineer or a land surveyor, who knows? Your boss might say, no, for our company, we just keep 3 decimal places always, because who knows? Someone might want to check your rounding later. They might say keep 5 decimal places if you have 5 decimal places. You got to do what the boss says, right? If that's the case, that's the case. This is just math. We're just having fun. I would stick to the same level of accuracy they have, and I would say we've got a hill that's 0.3 miles. And that might look like a really small number, but it is smaller than the hypotenuse, so that's good. And again, the hill didn't have a lot of slope to it. I even exaggerated the 6.5 degrees quite a bit. That 6.5 degrees is, very, very small in terms of the slope going up. So when they call it a hill, they do mean that is a very gradual hill, not some sort of mountain. But for the visual, I wanted to give myself some more space to spread out. So that seems like a fairly reasonable answer. We will go ahead and keep that reasonable answer. Let's see, moving on to another one. And I'll probably get to a good mix of examples, hopefully like 6 examples or so. That kind of give you a little bit of exposure to everything. I like number 21, which talks about the angle of elevation. So there's that word that we're talking about, elevation. If a 73.0 foot flagpole casts a shadow 51.0 feet long, what is the angle of elevation of the sun? And this one actually tells you to the nearest tenth of a degree. Notice that you've got 3 significant figures when you talk about a flagpole that is 73.0 feet. That 0.0 is significant. They're not saying that they only had whole feet to deal with and it was just 72.75-ish or 73.1, and then they rounded it to 73. No, they're being very specific that they could measure it down to that level of accuracy. Same thing with the shadow that's being cast. 51.0 feet. Sorry, you might hear my dog in the background. He's been barking at random stuff because he's a puppy. That's what puppies do. There's our shadow from the flagpole. What's happening is the sun is casting some light down on that flagpole. And as the light hits the flagpole, it's just casting that shadow down onto the ground. And again, there's the little nub on the top of the flagpole. Our task is to find the angle of elevation up to the sun. So I'm going to call that theta. Now, please don't ever look at the sun. I shouldn't have to say that. Hopefully your parents did a good job telling you that. Don't look at the sun. The sun will destroy your eyes. Also, be careful if it's a full moon out. You might look at the moon and go, oh, that's awesome, and you might want to stare at it for a while. Don't stare at the full moon for too long, because you're literally staring at the sun. That is just pure sunlight reflecting back into your eyes. It's not as bad as looking at the sun, but still, just throwing that out there. Little life lesson for you. Call that a pro tip. So let's take a trig function that involves this angle theta. What I'm looking at is the opposite side and the adjacent side. So of course I want to try and grab the tangent function. Tangent of theta is going to be equal to the opposite, which is 73.0, over the adjacent, which is 51.0. Now I have to grab theta out of that tangent function. So when I look at the tangent function, in order to undo that function, I mean we need the tangent inverse function. whatever I do on the left, I have to do on the right. So these need to match up. But the nice thing about doing tangent inverse of tangent, well, they cancel each other out and they return the argument theta back to me. And that's what I'm trying to solve. I want that angle. And again, it says to the nearest tenth, so we'll do that in the end. But we need to go to our calculator and type in tangent inverse of 73.0 over 51.0. In the calculator, you don't have to type the point zeros. It will actually look at it and go, I don't need that, though. That's the same thing as 73 over 51. So your calculator will actually do that reducing for you. But you can type them in if you want, just to be safe. Now, again, in the calculator, when you look for this function tangent inverse, you're going to have to hit the blue second button first. That will highlight the blue functions. In this case, above the tangent button, you've got tangent inverse. So I'll do the blue second button, then I'll hit tangent, and you'll see it pulls up tangent inverse. Remember, this notation does not say 1 over tangent. This is not tangent to the negative first power. We're not talking about exponents or powers here. This is just a kind of a borrowed notation that we use for inverse functions. And then I go ahead and I'll type in that ratio, 73 over 51, where, again, if you did just type in 73 over 51, it wouldn't hurt you because the calculator is not going to give you a different approximation if you put the point zeros in top and bottom. It knows it's just going to simplify that stuff anyway. So we get 55, well, let me tell you what the calculator says. 55.0606898. Yeah, we're not keeping all that stuff because it said to approximate to the nearest tenth of a degree. So when I look at these degrees, I'm going to look one to the right of the tenths place, which is a 6. That's 5 or higher. So I move over and I raise that 0 to a 1, and I'll say that the angle of elevation from the horizontal up to the sun is approximately 55.1 degrees. Again, seems reasonable. So again, when you're done with the problem, just check and see if you're satisfied with that answer. If you get a really weird answer like 0.002 degrees or something weird, then you'd have to round that to 0.0 degrees if you round to a tenth place. Obviously, an answer like that should not be satisfying. You know, check your calculator. Maybe you're in radian mode instead of degree mode or something weird like that. Or maybe you used the wrong inverse trig function. Or maybe you didn't use the inverse function. Maybe you typed in tangent of 73 over 51. Any amount of things can go wrong. So always double check your final answer. Just make sure you're comfortable with it. It's not ridiculous or anything like that. Next one, actually I'm going to scroll down to 23, which actually has a nice little diagram that we can follow. I'm still going to draw again sort of what they have. It might not look as pretty, but it'll be something that I can draw on and I can fill in the blanks. So it says a person standing 150 centimeters from a mirror notices that the angle of depression from his eyes to the bottom of the mirror is 12 degrees, while the angle of elevation to the top of the mirror is 11 degrees. So we know that we're standing 150 centimeters away from a mirror. The angle of depression, which maybe I'll do in red, is 12 degrees. And again, from our eyeballs, we're looking up. The angle of elevation to the top of the mirror is 11 degrees. Let me slide this 150 over, put that a little too close. There we go. And maybe we'll do the angle of elevation in green. So here's our eyeballs. We know we're 150 centimeters away. Question is, what is the height of that mirror? Well, you've already measured how far away you are from the mirror. Why didn't you just measure the mirror in the first place? Some math problems can be a little funny. It always gives me a chuckle. Someone took the time to actually measure how far away they were, but they were too lazy to take the tape measure and measure the height of the mirror. Well, that's okay. We can still figure it out. But I'm going to break it down into two right triangles. Remember, this is right angle applications. If you try and find that whole height in one shot, you're not looking at a right triangle. This angle, this angle, this angle, and this is the combination of two angles. Yeah, you can find it by adding those two together. That's just 23 degrees. But neither of these angles, the one down here or the one up here, are 90-degree angles. So we can't really use those trig functions right now. What we want to do is break it apart, and I'm going to call the height of the top piece from here to here x, and the height of the bottom piece y from here to here. And all I'll have to do is just combine x and y. Now, I'm going to do it one at a time. First, I'm going to go for x. I'm going to find that height x. If I want to do that, then I have this angle 11 degrees. So I'm staring from this perspective, looking up 11 degrees, and I have the length of my adjacent side. X is what I would call the opposite side. So again, adjacent, opposite, and that degree. I'm going to go for my tangent function and say that tangent of 11 degrees, by definition, would be the opposite side height x, which I don't know, and the adjacent side, well, that's length 150 centimeters. So to clean this up, we'll multiply both sides by 150, cancel, cancel, which will give us x to be 150 times tangent of 11 degrees. Now, since I'm going to have to add y to that, I'm just going to keep that. I'll do it later. I'll put it all in the calculator in one shot. We'll do the exact same process to find y. We'll get some sort of expression with a trig function in it. Since I have to add it to this anyway, I'll just do it all at once in the calculator. So to find y, we're going to take tangent of 12 degrees, which is the opposite, which is now y, over the adjacent, oh, that's the same adjacent side, 150 centimeters. So angle, opposite is y, adjacent is still 150. That means I'll multiply both sides by 150 to get that 150 to cancel out on the right-hand side. And now I know that y is equal to 150 tangent 12 degrees. Okay, thus, now let's bring it all together. The height of the mirror is x plus y, which means I can just go to my calculator and type in 150 tangent 11 degrees plus 150 tangent 12 degrees. So I just weighted in the end, and then we'll look at the significant figures and do some rounding when we need to. So 150 tangent 11 plus 150 times tangent of 12 should give us approximately 61.0405. Well, if we look at the 150, technically that's two significant figures. They're not giving us a specific order as to how many decimal places to go to or anything like that. So I would say we would round this to either 61 centimeters or 60 centimeters. We're losing that hundreds place, but this is really only two significant figures. We don't know if that was 149 or 148 or 151, and they were doing some rounding to a tens place. So we might not want to be that accurate and say, well, it's exactly 61 or exactly 62 or exactly 59. We might do the same thing and say, well, you gave us a measurement rounded to the tens place, so I give you a measurement rounded to the tens place. Again, this is just math, so we're just having fun. Again, check with your boss, see what they want. I wouldn't be super picky in this case. Or rounding anyway. who's to say who's right or wrong? So that 61.04 or something, we can round that to get an approximation. Our approximation is destined to have error built into it. Since this was pretty vague down to the tens place, I would still be careful in myself in a real world application. I would say, well, I only feel comfortable saying it's about 60. Might be closer to 61. You definitely don't want to go off on a limb and say, oh, it's exactly 61.04, whatever it was. Someone's going to say, how the heck are you being so accurate? You don't even have those marks on the tape measure. How can you see that? But yeah, technically that 150 is really just two significant figures. Even there is a 150. That last zero is not significant because we don't know if that came from rounding. Okay, that was 23. Next, I want to we'll pick on 28. I can get that to slide down. 28 does not have a diagram. Not all of them have a diagram that you can follow. So you do have to practice drawing things. A lot of this class is going to be drawing out a triangle to get your frame of reference. Once you've got your actual frame of reference, you can start wrapping your head around a word problem. So always for these word problems in math, read it once, just to read it. See if you come across any weird word like, angle of depression. Ooh, I forgot what that was. Let me look that up and then I'll come back to the problem. Or bearing, you're not 100% sure what bearing means. Go look that up and then come back to the problem. Then reread the word problem. That's when you should think, oh, okay, now I have to solve this. But the first time you read a word problem, don't even care about solving it or not. Just read it to read it. See if you can get any words you don't know out of the way. So number 28 says, a tree on one side of a river is due west of a rock on the other side of the river. From a stake 21 yards north of the rock, the bearing, there's that word, of the tree is south 18.2 degrees west. How far is it from the rock to the tree? Okay, so I just read through it just to kind of wrap my head around all the words. I'm comfortable with the words. So let's get a nice frame of reference going here. A tree on one side of the river is due west of a rock. Here's a river. Over here, I'm going to draw a tree. Yeah, it's not going to be the prettiest tree, but it's a tree. And that is due west of this rock that is on the other side of the river. You don't have to get very extravagant with your pictures, right? From a stake 21.0 yards north of the rock, the bearing of the tree is south 18.2 degrees west. So I'm going to go exactly 21.0 yards due north of the rock. And now I'm going to set up my cardinal directions north, south, west, east, and say that that tree from that stake that is 21.0 yards away is going to be south 18.2 degrees west. So I'm going to draw an angle here, and maybe I'll use red to represent that angle that is going south 18.2 degrees west. So again, we always measure bearing from the north-south line. They're starting off with south and then going towards the west 18.2 degrees. We also have 21.0 yards. That is the measure of the side going from the rock to the stake. And we also have the fact that the tree is due west of the rock. So I can move that north, south, west, east cardinal directions right on top of the rock and go straight west to get to my tree. That creates a 90-degree angle, which again, we're dealing with problems that have right angles. So we better have a right angle in there somewhere. And that's where it is, right at the rock. Question says, how far is it from the rock to the tree? Let's call that, since the river's kind of in the way there, I'll use blue as well. Let's call that X, the distance from here, the tree, to the rock over there. So, picture, if you give it too much detail, it might be a little confusing. It really is just a triangle where you have an angle, so your perspective is coming from up here at the stake, that angle 18.2 degrees. You have an adjacent side, and you have the opposite side. So if I'm at the angle up top, the adjacent side is the 21.0 yards, and I'm looking for the opposite. Again, it's another tangent function. Tangent of 18.2 degrees is going to be equal to the opposite, which is x, over the adjacent, which is 21.0. Multiply by 21.0 on both sides to get it to cancel. And we can go to our calculator and type in 21.0. You don't need the 0.0 on the calculator. Again, the calculator will just recognize that as the number 21 times tangent of 18.2. And since we're talking about yards, we get 6.90444. Well, look at, they're being accurate straight down to that tenth place. So I'm going to say 6.9 yards. If you said 6.90 yards, because it's 6.904, it would be a little more accurate as far as the finiteness of your measurement. I wouldn't mark it wrong, because technically you could argue, hey, that's three significant figures. If I did 6.90, that's three significant figures. But here we're losing the tens place. If we lose the tens place when we go from 21 just to a straightforward 6, it doesn't feel right to then pick up a much more finite level of accuracy. If I then lost the ones place, does that mean my tool that is only accurate to the tens place can produce a result that is accurate down to the hundredths or the thousandths place if I keep losing more and more value because I'm measuring something smaller and smaller? Again, I would argue no, but in the real world, hey, check with your boss. Your boss might say, keep every decimal that the calculator tells you, because we might want to go back and check your work in a year. But again, this is math. We're having fun. All right, let's pick on one that is a bit more three-dimensional. And we've covered some, or no, sorry, maybe not this one. Oh, it's the last one I want to do. I apologize, I jumped the gun there. I'm going to do one with the bearing again. So I'm looking at number 32. Number 32 says a boat travels on a course of bearing south 63 degrees 50 minutes east for 111 miles. How many miles south and how many miles east has the boat traveled? So sort of what they're doing is they're asking us to break this down into what are known as the components for the south and for the east. So since we're going south 63 degrees and 50 minutes east, I'm going to set up my cardinal directions here and let my boat travel south 63 degrees and 50 minutes east for 111 miles. Meaning that my angle is measured from the south line and I go eastward 63 degrees and 50 minutes. Now, what this generates is the vertical component and the horizontal component. Here, the vertical component is saying that the boat started somewhere and traveled a certain distance south to get to where it is now. and it also traveled a certain distance to the east to get to where it is now. So that's what we're trying to break down. How far south is it? Just south. How far east did it travel? Just east, not counting the south part. So I'm going to label X for the distance it traveled strictly to the east, just that one component, and I'll use Y to talk about the distance it traveled south, just that one component. This does generate a nice right triangle, since north and south and east and west are perpendicular to each other. Now, we all know that the boat started at some point and just went in a straight line to go 111 miles at this 63 degrees and 50 minutes. The boat itself didn't have to travel, and yes, that's my picture of a boat. The boat itself did not have to travel straight down, turn 90 degrees, and travel straight east. That's not what it's saying. But it's asking for just the south length, just the east length. So we have to break it down. And the angle that we're dealing with, maybe I made it a little large here, is this angle from the south line turning in eastward 63 degrees and 50 minutes. Don't worry about the minutes because the calculator can do the minutes. So let's say we want to first find X, which is the distance traveled east. What we'll do is we'll take that angle. From that angle, we've got an opposite side, which is X, and we also have the hypotenuse 111. So since I have the opposite and the hypotenuse, you guessed it, we're going to go for sine of 63 degrees and 50 minutes will be equal to the opposite from that angle is X over the hypotenuse, which is 111. That was the longest side. So 111 times sine of 63 degrees and 50 minutes is equal to X. And we'll go ahead and we'll see what X is. Now, the nice thing about the calculator is you can type in 111, then the sine function, then 63. Then you can hit the second button, which is our blue button, and there's a button that says apps, but right above that in blue it says angle, and that's why we hit the blue button to get the angle feature to pop up. That first symbol is the degree symbol, hit enter, and then we'll type in 50 and repeat that. We'll hit second apps to get to our angle menu, and number 2 on that list is the minutes button, so scroll down and hit enter to get the minutes in there, and that's always good practice to just close off those parentheses. And we get 99.624. Okay, we're just going to round that to 100. And since we're talking 99.6, we're rounding up to 100. The unit we're talking about is miles. Makes sense because if the hypotenuse is 111, that side needs to be smaller, and that is smaller. So that feels okay. Next we'll find Y. Same angle though. This time Y is the adjacent side. So from our perspective here, we're touching that adjacent side Y, which means I'm going to switch to my cosine function. But I'm still looking at the angle 63 degrees, 50 minutes. This time, when I'm using the cosine function, the definition is the adjacent side, which is Y, over the hypotenuse, still the same hypotenuse, 111. So we got 111 cosine 63 degrees, 50 minutes. Again, don't worry about the minutes. We'll approximate this all in our calculator. So off we go to our calculator. 111 cosine 63, same thing, second. Apps to get your angle list, hit your degrees. 50 second apps to get your angle list. Scroll down, hit the minutes symbol. This time, there's my marker. This time we get 48.949. Yeah, I'm just going to say that's approximately 49 miles. So again, that 63 degrees, maybe I could even exaggerate that a little further, because it's more than 45 degrees by quite a bit. So yeah, that distance traveled south should be a little smaller, definitely, than the distance traveled east. That should be a larger quantity. But that's all they ask us for is basically the components, just to summarize and make it all sound nice for who's ever reading. We would say thus: the boat traveled 49 miles south and 100 miles east. And then, let's see, 37 is a good one to pick on. And I think that should wrap things up nicely. Obviously, there are more examples in there that we can continue to go through. Maybe I'll do one more after this, just for fun. So 37 does give you a diagram, but again, I'm going to redraw it. It talks about the height of a tree. You can see their diagram, very detailed as far as like, ooh, pretty picture. But it doesn't have a lot labeled on it. So I'm going to redraw a picture and I'm going to label stuff a little bit clearer to my eyes. It says that an ecologist wishes to find the height of a redwood tree that is on the other side of a creek, as shown in figure 19. From point A, he finds that the angle of elevation to the top of the tree is 10.7 degrees. He then walks 24.8 feet at a right angle from point A to point B. There he finds that the angle between the line segment AB and a line extending from the point B to the tree is 86.6 degrees. What is the height of the tree? Let's take this one sentence at a time and get our frame of reference down. Being careful, because this really is like a three-dimensional picture that we have to draw on a two-dimensional surface. This is where you're going to probably need the most practice drawing things. And I'm not going to over-detail this one too much. I'm going to draw a vertical line to represent the height of the tree. I'm just going to remind myself that that's what I'm finding there. I am finding the height of the tree. And that's it. As far as pictures, like, fanciness goes, that's as fancy as I'm getting for drawing stuff. What I want to do is draw an angle that is, maybe that's a little too much. Draw an angle that is almost coming out of the board, and I'm going to draw an angle going up to the top of the tree. Now, what this creates is, when you start reading, the first sentence is really just a bunch of introduction. An ecologist wishes to find the height of a redwood tree that is on the other side of the creek. In the diagram, you can see there's a creek, water running here. The ecologist is on the near side. He doesn't want to get his feet wet. He doesn't want to cross that creek. The water's flowing too rapidly, and he forgot his boots. So he's thinking, oh, shucks, I'll never know the height of that redwood tree. Well, you don't need to be on that side of the river to figure out the height of that tree. You don't have to climb that tree with a tape measure or a rope or something like that. That's too dangerous. You can still find the height of that tree just using some trig. So first sentence is just a little introduction to get the picture started. Point A is where he's standing on the other side of the creek. And from that point, he finds that the angle of elevation to the top of the tree is 10.7 degrees. So, I gotta stop doing that. So 10.7 degrees is the angle of elevation, meaning he's measuring from the horizontal straight up and getting 10.7 degrees. He then walks 24.8 feet at a right angle from point A. So where he's standing, staring at the tree, he's going to turn 90 degrees and walk 24.8 feet away to what they are calling point B. Now that's a 90-degree angle. And then from that point B, he finds that the angle between the line segment AB and a line extending from B to the tree is 86.6 degrees. From line segment AB and a line from B to the base of the tree, he's going to find that he gets an angle of 86.6 degrees. So this angle inside here is 86.6 degrees. So now we've got two triangles. One of them is standing up, and what it's doing is it's producing a right angle, because we're assuming that angle of elevation that we're looking at, that flat ground, and the tree is growing perpendicular straight out of that flat ground. At least the trunk of the tree is, the very base is perpendicular. It may do some wiggles and wobbles till it gets to the top, but it's coming straight out of the ground. And then from point A, when he was looking at the tree, he turned exactly 90 degrees and walked 24.8 feet. So this is also a right angle, this angle at point A, for the triangle laying down. So this generates two triangles, and with those two triangles, is there enough information to figure out the height of the tree? Well, the triangle standing up, I don't have a lot of information. I don't have a hypotenuse. I don't have that opposite side from angle A. I don't have the adjacent side. I don't know any of the sides. Best thing I can do with that vertical triangle standing up is just find the third angle. But having just three angles doesn't tell me anything about the lengths of sides. So I can't do anything with that vertical triangle, but luckily I do have a length 24.8 feet for the line segment AB. That's actually helpful because that is a length of a side. It's the only length of a side that I have right now. And I have an angle on that triangle that is laying flat down. So luckily I'm on the near side of the creek, and I know that this angle 86.6 degrees and this adjacent side to that angle 24.8 feet, I can cook up this shared side between the two triangles. What will that do for me? Well, it will help me translate from one triangle laying down to another triangle, the one that's vertical standing up. Once I have that length of that shared side here, I have one of the sides of the vertical triangle, which also I have an angle, which means I can find at least one of the other sides using some trig functions. So I'll start by taking this angle, 86.6 degrees, the adjacent side, and this is the opposite side, x. I'm just calling it x, that's our shared side. I'm going to find x first. Meaning that I'll take tangent of 86.6 degrees. By definition, that will be the opposite, which is x, over the adjacent, which is 24.8. We'll multiply both sides by 24.8. And that tells us x. I can put that in the calculator and approximate it, or since I'm just going to use it to get to what I really want, why approximate this and then use an approximation to approximate h, when I can just simply put this in my calculator to then find h. So I'm just going to leave that and say that I can find h second, because now I can transition from the triangle laying down to the triangle standing up. I have an angle, 10.7 degrees was my angle of elevation. I'm stealing this x and now calling x the adjacent side for the angle A, that's the angle of elevation, and I'm looking for the opposite side, which is h. So now I'm looking at a triangle that is standing up. I'm done with the one laying down, and I can say that for that angle, I have tangent of 10.7 degrees is going to be defined by the opposite, which is h, over the adjacent, which I just found was 24.8 times tangent 86.6 degrees. So again, I'm just waiting to put it all in the calculator once rather than have to pick up the calculator twice. If you approximate this and then use the approximation in your calculation, you'll be so close it's not even going to make a difference. The more decimals you keep, the closer you'll get. But to not really mess anything up, I'll keep that exact value, 24.8, tangent 86.6 degrees. Multiply that on both sides so that the left-hand side becomes everything in terms of 24.8 times tangent 86.6 degrees times tangent 10.7 degrees. All I have left is h. Now we'll pick up the calculator and just let it do all the remaining work. So 24.8, tangent 86.6. Make sure you close those parentheses off because you don't want a tangent function buried inside of your other tangent function. That's going to be really weird. So close off those parentheses, then do another tangent function, 10.7. And again, it's just good practice. Close off that parenthesis too. Let yourself know that you're done typing everything in. We've got 78.87444983. So, okay, let's go ahead and say that the height of the tree is approximately, see how they've got three significant figures there? We'll stick with 78 point, I'll round that 8 up to a 9. And this one is, oh, let me look at the unit. Yeah, it was feet. Oh, I had it right there. Hello. There's our 78.9 feet. Let me see where we're at. We're at 56 minutes here. And we'll pick on one more. It'll be a quick one, though. You can see there's some more examples of the more three-dimensional figures that use two triangles. Sometimes they'll bring the bearing into the picture. More flagpole stuff. You can see that they're kind of running out of examples as far as like being at sea and shadows of flagpoles. Here's a good one. Not 42, is it 41 I guess is referencing? Yeah, 41. Talks about the radius of Earth. This one's a little different because at least it's got a circle in there. It says a satellite is circling 112 miles above Earth, as shown in the figure. When the satellite is directly above point B, angle A is found to be 76.6 degrees. Use this information to find the radius of the Earth. So I'm going to redraw the figure because, again, I want to see if I can get some space and fill in some information, play around with it. So there's our Earth radius. We're going to go straight up. That's what they're calling point B. We're going to keep traveling above the surface of the Earth another 112 miles to get to point A, where the satellite is. And then they say we have 76.6 degrees before we hit this point. I'm going to write 76.6 degrees, but I'm going to write it outside to represent, and maybe I'll do a little color here, this angle. That they're talking about. So what they want us to do is approximate the radius of the Earth. Well, we've got this 90-degree angle here that we can see in the diagram. Or sorry, how did I? Oh, I see what I did. I put the 90-degree angle in the center. Let me go ahead and fix my diagram. There's our radius. There's our 90-degree angle. There we go. We still have B and A, but that's our 90-degree angle. Still have our radius here. Oh, I think I switched the colors. Let me not do that. This is 76.6 degrees. It's angle in here. And this is our radius. those are the same R, since of course we're just going to assume the Earth is just a nice circle. Oh, and I forgot the 112. There we go. Okay, nicer diagram. Here we have an angle. I'm looking at an opposite side, and this is the hypotenuse, all of 112 plus the radius. Obviously, my scale is not, close here. It's just a general picture. But make sure that you see the hypotenuse as the entire length from A all the way to the center. That means when I look at this, I can say that if I've got an opposite side from that angle 76.6 and a hypotenuse, I'm looking at the sine function. If I take sine of 76.6 degrees, it would be the opposite, which is R, over the hypotenuse, the longest side, which would be 112 plus R. It wouldn't just be 112, it wouldn't just be R, it's the hypotenuse, it's the entire length from point A all the way to the center. Well, we can multiply both sides by 112 plus R, so that our left-hand side becomes 112 plus R times sine 76.6. On the right-hand side, if we multiply by 112 plus R, it cancels the denominator out. But we can't leave this as a solution. This is R, and this is also R. It's not a number. We haven't found the number that R has to be. So we'll have to do a little bit more cleaning up. Believe it or not, this is just a linear equation in terms of R. So all we have to do is get all of our R's on one side. We'll get 112 sine of 76.6 degrees plus R times sine of 76.6 degrees is equal to R on the right-hand side. I'm distributing, but I'm just distributing from right to left across that binomial, 112 plus R. Okay, this gives us something where we want to get all of our R's on one side. So I'm going to subtract R times sine of 76.6 degrees on both sides. I can barely fit it in there on the right, but I want to cancel it out. I can't just subtract R because R is being multiplied by this number. Whatever sine of 76.6 degrees is, it's just some number that I'm multiplying by R. So I'm going to subtract that whole quantity over at once. So I've got 112 sine of 76.6 degrees is equal to R minus R times sine of 76.6 degrees. Now I can't say that that is 0 times sine 76.6 degrees, right? Multiplication first. R times the sine of 76.6 degrees. Then I could do any sort of subtraction. So that's not the way we want to go about it. We want to factor out what we call the greatest common factor on the right-hand side, that being R. So I'm going to write 112 times sine of 76.6 degrees on the left. I'm going to factor out the common R. The remaining factor will be 1 minus sine of 76.6 degrees. Please don't factor out R and just leave sine 76.6. You need the 1 minus sine 76.6 because R should be distributed across both those terms, across subtraction. If you drop that subtraction, then you have a completely different right-hand side, and you've just lost your equation. You've lost the equality. Nice thing here is sine of 76.6 degrees is not 1, so this is not 1 minus 1. Basically just meaning that is not 0. So I can divide by that non-zero quantity, 1 minus sine of 76.6 degrees on both sides. I know I'm not dividing by 0 here, so I can say, let's divide to isolate R. Meaning that we can now approximate R by going to our calculator and just letting it do all the heavy lifting. We've got in the numerator, 112 times sine 76.6. Make sure you close that off. If you're on an older TI-83 calculator where you don't have that numerator denominator nice math print going on, you're going to want to do the division symbol and then put an extra set of parentheses. Since you've got two terms here, you want to keep them both in the denominator so that you can divide by 1 minus sine 76.6. You should get approximately 4,001.999999. We'll just say 4,001. 0.999. Well, let's say 4,002 miles. They had 112. We'll just say 4,002. That's good enough. And that is close. Depending on where you are on the surface of the Earth, though, I'm truly going to exaggerate it here, but if you look or try and do some more accurate measuring, because the Earth rotates and spins, it sort of like squishes itself out a little bit wider. So if you're measuring from like here out to the equator, you might get a slightly larger distance than you would from the center of the Earth up to the North Pole or down to the South Pole. Planets do this. It's not just an Earth thing, right? Almost every planet has some degree of what they call oblateness to it. I think Saturn is the most oblate planet. Don't quote me on that. Right? I don't know. I'm not an astronomer or anything. But because it's got all those rings which have gravity that kind of pull Saturn, and all those, tons of moons, it's kind of stretching the planet, making it wider than it is taller. So kind of fun. But obviously for mathematics, we've got to make some assumptions to simplify the things that we're doing. Otherwise, these calculations could be 100 miles long. And that's what we're doing. We're just assuming that Earth is a sphere. So that's kind of nice because it throws at least a circle at us, which is a little different. Yeah, I think that's a good plethora of problems that we could see as far as applications go. Obviously, practice everything you come across. Every problem's a little bit different when it comes to word problems. So that wraps up 2.4. Again, I'm sorry I missed you in the live section, but this is where I would say, hey, any questions? Email me. Let me know if you have any questions. Or if we have some time, we'll finish up 2.5, which talks a little bit about vectors. And then if we have some time, maybe we can go back and hit some study guide problems or talk a little bit more if you guys have questions about elevation, depression, or bearing, or anything like that. So thank you very much for watching the video, and I will see you guys soon again. Well, not physically see you, but I'll see you through the internet again soon. Let me know if you have questions. Otherwise, have a wonderful day.